Back again, doing CLEP, calculus, practice, exam questions from ones that I downloaded online from these URLs, also linked in the description. And we are going to jump right back into it with the next page. Again, we have some that were completely identical to the other exam that we already ran through. So we're going to jump to the first new question. That is going to be 34. And it says the function f is continuous in a closed interval from 1 to 5 and has values given in the table above. There we go. If two subintervals of equal length are used, what is the midpoint Riemann sum approximation of the definite integral area under the curve in that interval we were given of just the function? Okay, so we discussed Riemann sums before a couple of times, but as a refresher, if you don't know what the integral is, the definite integral, you don't know how to do that, haven't been taught it yet, hasn't been discovered yet, and you want to try to come pretty close to the area under the curve, you want to find it in some way, estimate it, you could take the values, pick out several evenly spaced x values and calculate the y values at each of those points, and then draw some nice little rectangles at the height of those points, and then take the heights of all the rectangles, add them together, multiply by the width of the rectangles, which should be the same, drawing not to scale, and you add all those together, and that gets you an area that is pretty close to what that area under there is. So what do we mean by midpoint? Well, when you are doing this with those points, you have a couple options as to how you're going to draw the rectangles. If you have your points there, if you draw your rectangle out to that side, that would be a right-handed Riemann sum, or Riemann sum, I'm not even sure how it's pronounced. If you were to draw the rectangle going the other way, that would be considered the left-handed Riemann sum. And actually what I drew here is the midpoint where you're drawing the rectangle around to both sides of those measured values that you are using. So let's examine what it's asking us again. We have the interval from 1 to 5 and two subintervals, meaning two rectangles of equal length, obviously equal length because the Riemann sum, it's always going to be equal length. So we have 1, 2, 3, 4, 5, and it told us the interval we care about is 1 to 5. So if we're going to divide that into two rectangles, well, we can do it you can do it just by looking at it, but mathematically it's 5 minus 1 equals 4 wide. And if we're going to subdivide 4 into two rectangles, that means they're going to be 2 wide. So the other one is going to be at 3. Those are the boundaries of our rectangles, 1 to 3 and 3 to 5. And we want the midpoint Riemann sum, which means the values that we want to evaluate, where we plug in x and find the height of the rectangle, is going to be at the midpoints of each of these, so 2 and 4. So now they give us a nice little table. So at x equals 2, we have a y value, or a rectangle height, of 10. And at the x value of 4, we have a f of x, or a y value, of 6. And the other ones don't matter because we're not checking those. If we were to use narrower rectangles and use each of those values, we would get a better, more accurate approximation of the area, but it would also take us longer because we'd have more numbers to add up and so forth. So they kept this one simple, make us only have to work with 2 of them. But okay, so what do? We're going to add the heights together. 10 plus 6 times the width, which again we said is 2. So 16 times 2 equals 32. And would you know it? There's a 32 right there. That is going to be our answer, selection D. Okay. 35 we've done before. 36, 37 we've done before. Here's the next new one, number 38. If the function is the natural log of the sine of x squared, then the derivative of all of that mess is going to be what? And oh my goodness, wouldn't you know it, it is the chain rule. It's not just a chain rule, it's a double chain rule. We have to chain rule twice. That's crazy. But okay, let's just take it one at a time. Now, in a normal chain rule, you have the function f of the function g of x, and take the derivative of that. You have the derivative of f with the original g inside times the derivative of the g. So we can do maximum 2 at a time. So let's work it from the inside out. So we're just gonna do the inside 2. We're gonna do sine of x squared. Sine of x squared. So our f in this case is sine of x. Our g is x squared. G inside of f. So the derivative of f, derivative of the sine is cosine. Derivative of g, derivative of x squared is 2x. Bring the 2 down, subtract 1. Probably the one of the easiest ones there is in terms of the power rule. And how do we find that? Well, we're going to take the derivative of f. That's cosine. Inside it is going to be the original g, x squared, and then it's going to be multiplied by 2x. And just for a little ease of use, let's rewrite that. 2x cosine of x squared. So we like to have that kind of thing out in front. Okay. And then this is that's the derivative. That's the derivative of that. And so if we consider the original thing, where we have the natural log of the sine of x squared. Now we are going to consider our f to be that natural log, and the g is going to be what's inside the natural log, the sine of x squared. And so the derivative of natural log is 1 over x, and the derivative of the sine of x squared is what we did up here, 2x cosine of x squared. So now we take all that and plug it into the chain rule formula again. Let's rewrite it just to remind ourselves. So we did the inside first, just so that we could find the derivative of that when that whole thing is our new inside. So we have this, we have the derivative of that f being 1 over x. So we're going to be 1 over something with the original g, which is that sine of x squared. So 1 over sine of x squared multiplied by the derivative of the g, which we just determined was the 2x, and we'll just go ahead and put it up on top of there. 2x cosine of x squared, and well, the 1 goes away, so never mind that. 2x cosine of x squared over the sine of x squared, and does it give us something that looks like that? It certainly does. 2x cosine of x squared over sine of x squared. That is indeed the answer. And again, if it throws something complicated at you, just break it down, take it by the steps, work it from the inside out, and it ends up being not as complicated as you would think at first glance. Okay, moving on from there. So again, 39 we've seen before. 40 is our next new problem. So we have a rectangle with one side on the x-axis, it's just flat against the bottom, and one side on the line x equals 2. So yeah, we can see from the diagram it's just at x equals 2. And the upper left vertex, meaning that corner, as you can see in the picture, on the graph of y equals x squared, is just describing what's in the picture, as indicated on the figure above. It's a lot easier. If they just describe this to you, you'd have to draw the picture so you can see what they're talking about. But they give you the picture for what value of x, meaning, where here does the area of the rectangle attain its maximum value. So it's somewhere along there. At what value of x for that other side is the rectangle going to be the biggest? Okay, so the area is the base times the height. So what is the base going to be? Well, the base is this, so it's 2 minus x is the width of the rectangle. So 2 minus x. And what is the height? That's this much, so it's just the value of the function at x, which is x squared. So the height is x squared. And we can distribute the x squared through there. 2x squared minus 3x cubed. Just x cubed, not 3. Okay. And so, as per usual, when you have an equation and you want to find where it is the largest, we want that maximum value, so we're going to assume it has a maxima somewhere. If we were to, y equals that and put it on a calculator, graph it out, it would have some maximum somewhere. And at that maximum, as with all maximums, the slope would equal to 0. And we can figure out that. We can get the equation for the slope, which is just the first derivative. So we'll take the derivative of that, bring the 2 down, multiply by the 2, get 4, subtract 1, just get x to the power of 1, so we just write it like that. And then minus, bring the 3 down, and 3 minus 1 is 2. So that's the derivative of the area. And then we want to know where the maximum for that is going to be. And let's simplify it just a little bit. We can pull an x out. And so where is that equal to 0? Well, if x equals 0, that would be a maximum of you know, it would be the slope equals to 0, but that is definitely not going to be where the rectangle is biggest. So we're going to ignore that. We're going to toss that out and just deal with 4 minus 3x. And we'll add 3x to both sides, and then divide by 3. X equals 4/3. And that's all we need to do. X equals 4/3. You know, find the value of x. 4/3 is an option there. Choice B for number 40. And that is correct. All right. Number 42. If f is continuous for all x, which of the following integrals necessarily have the same value? Isn't that a fun question? Okay. So, just the standard definite integral from a to b. So if we took the integral of f and filled in the upper bound and then subtracted the integral with the lower bound, we would get something like that. And then if we took the integral of that, so if it was something like, now this is in terms of x, so we would take that upper bound and fill it in for just the x. This is kind of weird how it's done, but you know, roll with it. It's weird, but you just roll with it. So you would fill in the b minus a for the x, but there's still a plus a, so we're going to carry that over. And then we are going to subtract the lower bound where x is 0, but we still have that a. And then if we actually calculated that through, minus a plus a, we're just left with the f of b, and 0 plus a, we're just left with f of a. So that actually looks the same as that. So we're starting to look like Roman numeral 1 and Roman numeral 2 do have the same value. So let's check Roman numeral 3. What's that one going to look like? Okay, so if we took the integral here, we're going to take the integral and fill in, again, that upper bound for x. B plus c goes into x. B plus c plus another c minus the integral where you filled in the lower bound, a plus c, and then carry through that other plus c, and we get something like fb plus 2c minus fa plus 2c, and whatever the heck c is, unless C is 0, that doesn't match that, so we can't say it necessarily has the same value. So it just looks like we're only looking at Roman numerals 1 and 2 of being what we know for sure are going to be the same value. And that is the answer for that one. Okay, and 43 we've done before, 44 we've done before, and on the next page all we're left with is 45. We've also done that one before, so that is the end of that one. And that is the end of both our tests, but I think I'm going to do one more video just to kind of do an overall review study guide, based on all the problems we've been through, of just what are the key main things that you need to know, remember, memorize. So that will be in the next video, which should be the final video, and see you then.